So, when last we spoke, we were talking about this problem right here. The integration, the definite integration of an absolute value. Now I had said the first thing you need to notice is that the absolute value is actually a piecewise function. Piecewise function that says whenever the thing inside the absolute value is greater than or equal to 0, leave it as it is. But anytime that thing inside the absolute value signs is less than 0, take the negative of it. So we're always forcing it to be 0 or greater, right? That's the point of it. That's what it does. So with that, what our problem says is we've got 2x minus 1, the absolute value of that, so since 2x minus 1 is playing the role inside of this, right? It's playing the role of x as it was up here. We're going to have 2x minus 1 wherever there's an x here. Makes sense what I mean? 2x minus 1 greater than equal to 0. 2x minus 1 less than 0. So a review of piecewise functions, in case anybody's forgotten anything about what a piecewise function is a function that says do a thing for a certain part of it, given a particular set of rules, right? Do another thing, give it another set of rules. Do another thing, give it another set of rules. And you can have a piecewise function as long as you want, right? So this is just one example of a piecewise function. Having said that, how are we going to rewrite this now? We need to know some details about when to do these things. Well, we know that we're going to be 2x minus 1 whenever 2x minus 1 is greater than or equal to 0. And negative 2x minus 1 whenever 2x minus 1 is less than 0. But we want to write these rules now in terms of x, right? So we have to solve these inequalities. Well, notice all we really have to do is solve just one of them because the other one will give us that other case, right? So we got 2x minus 1 is greater than or equal to 0. Add 1 to both sides. Divide both sides by 2 now. And we've got whenever x is greater than or equal to 1/2. So we can rewrite again to find that this thing is equal to 2x minus 1 whenever x is greater than or equal to 1/2 negative 2x minus 1 whenever x is less than 1/2. Okay, now why is this important? This is important because we're integrating from 0 to 2. This absolute value sign, or this absolute value of 2x minus 1. And because 2x minus 1 is a piecewise function, it means it's not just really one function, it's a bunch of functions stitched together, right? And we have to integrate each one of those individual functions separately from the others. So we have to break up a piecewise function to integrate it under a definite integral. Does that make sense what I mean? So now that we know 1/2, well, let me write it out this way. 2x minus 1 dx. Now that we know 1/2 is the value that separates our two different parts, we know we're going to have to break this integral up from 0 to 1/2 and 1/2 to 2. Make sense? So this is going to be equal to the integral from 0 to 1/2. Well, 0 to 1/2, we're going to be negative 2x minus 1. Yep. Dx. Now we're going to add the other part. It's going to be 1/2 to 2. We're going to be 2x minus 1 on that interval. Now, just to show visually what we're doing, we are finding the area from 0 to 2 underneath y is equal to 2x minus 1, the absolute value. So we're finding these two triangles added together, the area of each of these two small triangles, putting them back together, right? So having said this, I'm going to let you all work on this and solve it really quickly on your own. While you all are doing that, I'm going to step out for just a second. I'll be right back. so where are we with this problem? Did anybody get 5/2? Folks at home, did any of y'all get 5/2 for this problem, for the solution?
I did it, but I think I did something wrong.
I think you might have done something wrong. All right, so let's see what's going on here. So, I've got room here. So looking at this problem, we're going to do these things in steps, right? First, we're going to do the integration, and then we're going to apply the bounds. So this first integration here, well, we pull out that negative sign. When we do, we're going to be integrating 2x minus 1 with respect to x. So this is going to be 1/2 times 2, here, let me write it this way, 2x squared over 2, right? Minus x with the bounds 0 to 1/2. Now we're going to add this other integral, but it's really just going to be the same thing, just without this negative, right? So let's go ahead and do that. It's going to be 2x squared over 2 minus x, this time from 1/2 to 2. All right, we've got some cancellations now. We can cancel out these 2's. When we do, what we're going to be left with is negative x squared minus x from 0 to 1/2 plus x squared minus x from 1/2 to 2. Okay, now here we might be tempted to try and cancel things out, but we can't. Because what's happening here is we're saying, evaluate these things from 0 to 1/2, and evaluate this thing from 1/2 to 2, and then add the two things together, right? The two sets of solutions. So what we have to do is we actually have to calculate those bounds first. So we have negative x squared minus x from 0 to 1/2 plus x squared minus x from 1/2 to 0 or to 2. I apologize. So this first term is going to give us negative, let me write it a little bit different. This will work. Negative 1/2 squared minus 1/2 minus negative 0 squared minus 0 plus, now we're doing these, so let me try and organize this so that we can see what's happening. plus, now we're doing these over here. This is going to be 2 squared minus 2 plus 1/2 squared minus 1/2. That's everything, right? So now we have to simplify all of this, do the algebra. Here, we're going to get negative (1/4 minus 1. We can rewrite this 1/2 as 2/4 minus negative. Well, all of this is just going to be 0. Let's ignore it, right? Let's just leave it like that. Actually, let's leave the 0. Just keep track of terms. Plus, coming over here now, we've got 4 minus 2 minus, I miswrote this, I meant to write minus up here a minute ago, minus 1/4 minus 1/2, or we can rewrite that as 2/4. Looking at this, we can rewrite this as plus 2 minus 1/4 minus 2/4. It's going to be negative 1/4. So that's like adding 1/4. Agreed? That's just done over here. Now coming over here, minus times 1/4 minus 2/4. This is going to come out to be negative 1/4 times that negative. It's going to be like 1/4 again. I've done something wrong. Where did I go wrong? I did it. That's right. Plus the 0 plus. So moral of the story here is everybody makes mistakes, and it looks like I did not hear. Did I? 2. That's right. That's right. That's right. So maybe I'm just doing something wrong in my head right now. All right, so putting all of this together now, we have 1/4 plus 2 plus 1/4. Okay, I see why. Yeah, I'm right. Cool. So this is going to come out to be 1/4 plus this 2 can be rewritten as 8/4 plus 1/4. Adding all of this together is 10/4, which is equal to 5/2. So, a lot of calculations going on here. And like you just saw, it's easy for anyone to lose track of all of this stuff. It helps to try and organize things and do parts of the arithmetic as early as you can. Make sense? So how does this problem feel from start to finish? What do y'all think? After a time or two with it, think you could figure it out? Yep. Now, I want to point something out. The rule we used here is one of the properties of integrals. The reason why we're able to break this integral up the way we can, or the way we did, it comes from a very particular rule. And it's not obvious until we see the geometric interpretation why it happens this way. So let's say we're integrating from a to c of some function. Well, we can break this up as a to b, the integration from a to b of our function with respect to x, plus the integration from b to c of our function with respect to x. Now, the reason why we can bring this up is because what the definite integral tells us and the geometric interpretations that come with it. So, coming back to just what this thing's doing. We've got a function like something like this, blah-de-da. Nothing too exciting yet, right? But we're going to integrate this thing from A to C. That's going to be this part, right? Now we're going to break it up and say, hey, there's a b inside of here. Call this thing b. It's going to be like right there-ish. It's going to break this integration up into two parts, right? So this first integral tells us the area from A to C. Now we're going to break it up, like I said, A to B, B to C. What this new integral tells us is just the left part of it. And what this right integral tells us is just this part of it. So, since the integral from A to C tells us the entire area, we would expect this integral plus this integral to add up to that, right? So as a geometric interpretation, we can think of the integration and breaking it up as breaking up the area into two different parts. So it should add back up to be the same thing. Does that make sense to everybody at home? Folks at home, does that make sense?
Yes.
Yes? Awesome. Cool. All right. So, having said all of that, and seeing this problem, let's move on to the next slide, which is about marginal analysis yet again. So, in the past, we said a marginal of cost, profit, and revenue was the derivative of that thing with respect to x, right? And what that's going to look like is, let's say we have a profit function, p of x, it equals blah, 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 whatever. The derivative of it was called the marginal profit, right? we use this thing to measure the change in profit, right? We said this thing times the differential is approximately equal to the change in P, given that X changes according to the differential, right? It's approximately the same. We can do one better now. Because of the integral, we can say, hey, if we integrate dp dx with respect to x, we get P back, right? And if we add bounds to it, so let's say from A to B, then we get bounds from A to B over here, and that becomes P at B minus P at A. The actual change in profit. So the definite integral of a marginal will tell you what the actual change of that function is from A to B. Make sense what I mean? So it's a little bit better than saying dp dx times delta x, right? Like it's a better approximation than this. This was just an approximation. This is an exact solution. Make sense what I mean? And in the past, this is what we used. So that's close enough. Except when the change in x gets really large, it starts to change really fast. It starts to become really inaccurate. Using the definite integral is an exact, precise solution. So the first time with an approximation, this is the exact. That's what I'm trying to say here. So having said that, we've got this example where we're given a profit function. dp dx is equal to this really dumb decimal. Why do they like decimals so much in this book? Every time I see a decimal, I'm going to complain about it. Just, I have to. Okay. So we've got this profit marginal. Now we're going to integrate this thing from 100 to 101 to answer this first question. For those of y'all at home following along in the slides, this is slide 30 and week 13 notes. You can find it under exam 4 in the course material. We're going to integrate this now from 100 to 101 100 to 101 of this ridiculous decimal 12.1 or 0.2, I mean, dx integrating this, we're going to hold off on the bounds, put those off to the side, right? And get negative 0.0005 x squared over 2 plus 12.2 x from 100 to 101. We can go ahead and simplify this a little bit to get negative 0.00025 x squared plus 12.2 x from 101 to 100. This is the same thing. I'm going to use abbreviated notation now. This is the same thing as saying your profit margin from 100 to 101. Same thing as saying this, right? I'm just using abbreviated notation now because I'm not actually going to go through and do the algebra. What's important is that we see what's happening up to this point and understand that. The second part is from 100 to 110. So all we're going to change really is our bounds, right? The integration stays the same, so our bounds are changing here, and that's it. So part of the point that I'm trying to illustrate here is doing this integration first will sometimes allow you to skip steps down the road. You don't have to do the integration a second time once you know what the P of X is going to be, right? Once you know what this thing is, you're good, you're golden. You've done this. Now if you need to do it again with different bounds, keep the same thing. As long as you're not using a piecewise equation, you're good. Make sense? So, having said that, checking out the way they go about this problem. They integrate dp dx with respect to x from 100 to 101. Do that integration, they apply the bounds. And they get that the change in profit is 12.15. From 100 to 110, they get that the change in profit is $121.48. It's a hell of a jump. So now, new idea. Now we're going to talk about the average value of a function on an interval. And I'm going to ask a really dumb question, because I'm sure I know the answer. Have you ever looked at a function and said, I wonder what the average value of that function is between these two values? So let's consider, for example, we've got a function that looks something like this. Have you ever looked at that and said, I wonder what the average value is? If so, congratulations, you find yourself in good company because plenty of mathematicians have in the past. And that's what motivates this question is how do we find the average of this thing? So this thing is going to be like f of x, right? It's a function. And if we, for a second, step back and think about this and what we can do based on calculus, we know we can find the area of this thing, right? This is the area from A to B. We can find the area of this thing. We say, hey, now, this thing's not a square, obviously. Obviously, it's not a square or a rectangle. But I feel like I just tried out for a Captain Obvious commercial. This thing's not a square. No shit. Thank you, Captain Obvious. Okay. So the function looks something like that. And I'm saying from here, somewhere over here, A to B. But let's imagine we wanted a square with the same area and the same base length. So the length has to be from A to B. The height of that is going to look something like this now. Like this. Let me, for the sake of drawing this clearly. Okay, so this square is going to have the same area as this integral. Well, the height of this square is going to be equal to the average value of your function on this interval. Make sense? So this thing is going to be equal to A to B f of x dx, but it's also equal to, let me write it another way. It's also equal to h times b over a, right? Or b minus a, I mean to say. Okay, so we know these two areas are the same. We know that h is going to be equal to the average of your function, right? So setting these equal, we get the integral from a to b of f of x dx is equal to h times b minus a, because these areas are going to be equal, right? The best part of this class is getting to draw pictures. So if this is the case, then what this is telling us is that the average value of our function is equal to 1 over b minus a times the integral from a to b of your function. And this brings us to the average value of a function on a given interval. If our function is continuous from a to b, then the average value of that function is going to be the integral from a to b of your function times the difference between a and b. Everybody cool with this? Folks at home, what do y'all think? Cool with this?
I'm with it. I like it.
With me? Cool. Dope. All right, so one possible application, Karen goes walking through Walmart over a 2-year period of time, and she's like, yo, I don't have anybody yell at. There's no managers around, so I'm going to keep track of how much the CD player costs. She does it once a month. And she comes up with a model for the cost of the CD player over this 2-year period, because that's what Karens do. If I have a Karen in my class, I apologize. I don't know your middle names. All right, so we've got this cost function with respect to time of 0.00. Damn, Karen, why are there so many zeros? 0.005t squared plus 0.01t plus 13.15, and time is from 0 to 24. So time is measured in months, and this is over a 2-year period of time. So this notation, just as a reminder, is the same thing as saying the square brackets mean you include 0 and 24, and time is somewhere inside of there. So that's just like saying time is between 0 and 24, and it can be 0 or 24. Okay, so we want to find the average value of this CD player over a 2-year period of time. So throwing it back to the 2000s, the early 2000s, we've got the integral from 0 to 24 of our function dt times 1 over 24 minus 0, right? So we can write this now as the integral, or my mistake, as 1 over 24, the integral from 0 to 24. I am not rewriting this function because it's just too long. ct. dt. But just reducing the fraction out front. We just do this integration and multiply by 24 at the end. Everybody cool with that? So this is going to come out to be 1 over 24 times, I'm going to write this in a funny way, but it's only so that we can see what's happening. 0.005 t cubed over 3 plus 0.01 t squared over 2 plus 13.15 t from 0 to 24, close that. Okay. So I wrote it this way just so that we can see what's actually happening inside. First, we're going to do that integration. Then we're going to apply the bounds. And then we're going to multiply by 1 over 24. So the 1 over 24 comes in at the very end. However, if you wanted to, you could go ahead and just pass it through and then do the calculations. But the point is that you don't want to do it term by term. You either want to wait till the very end or do it right here, right now. Everybody cool with this? Cool. So what we're finding is the average value of this function. We're saying, hey, what's the area underneath it? Now we want to find a rectangle with the same area and the same period of time. That's going to give us the average height. And in doing that, what we find is this is where the calculation takes us. After doing the algebra, this thing's going to come out to be 14.23. Let's say 16. Yeah, we've got time. We've got time for one more concept. So this next part is about even and odd functions. Even and odd functions are going to help us just do simple It's the only way to help us make problems easier for us to solve. So, what I'm saying is an even function. We start with the definitions of these things. Even, this means that f of x is equal to f of negative x. What this looks like are functions who appear to be reflected across the x-axis, the y-axis. So a common example of this would be everybody's favorite x squared. Now, an odd function is a function such that f of negative x is equal to negative f of x. These things are a little bit harder to spot by looking at them on the graphs, but once you know what you're looking for, they're pretty simple. These things are functions that look like reflections across the y-axis and then across the x-axis. That's a pretty common example of this. Pretty common example of this would be x cubed. Now, the reason why these are called odd and even functions has to do with the way they expand out. What that term expand means is something outside the scope of this class, but it has to do with the way they expand out. What it means to expand a function out is you take it up into, you turn it into something that you can add a bunch of to get the original function back. The expansion is just breaking it up into a series and saying, all right, all of these add up to our function. When you do that, even functions have only even parts. Only the even terms get left over. Odd functions, only the odd terms get left over, assuming certain things about the expansion you're using. So, why these are important is because they have some nice properties. If you integrate an even function from negative a to a, that's going to be like 2 times the integration from 0 to a of that function. In the case of an odd function, it's not quite the same. It's actually even better. An odd function, when you integrate it from negative a to a, let's look at this picture really quick. Here, we're going to get positive area, right? Here, we're going to get negative area. They're going to be of equal value. So when we add them together, they're going to cancel out. It could be just 0. And this is why we care about odd and even functions. Now, another reason why these things are useful is, let's imagine we have an integration of an odd function from, say, I don't know, negative 1 to 2 of an odd function. We can bring this up from negative 1 to 1, 1 to 2. That part's going to disappear. We're just going to be left with that 1 to 2 part. So these are useful tools useful observations for integration. Make sense? This is a really great tool to use down the road because it lets us simplify our work a lot. As an example of how it might, think about like a polynomial. We throw 0 through a polynomial, we either have a constant term or 0, right? So we only have to worry about the a part. Everything else drops out when we throw in 0, right? So it reduces the algebra down the road. This is one reason why it's useful. The other reason is, I see an odd function, I have to integrate it across something that's symmetric, -8 to a. Hell yeah, that thing's gonna turn into 0. Make sense? So, trick of the trade, some observations that help to reduce our work a lot. Having said that, I think that is time. That is time. So I will let y'all go. Have a good one, everybody. I'll stick around if y'all have any questions.